Hello, everyone. So, this is going to be a brief overview of three-dimensional modeling in STAR-CCM+. To date, at least this semester as of filming, what we've been looking at is two-dimensional modeling. We've done this primarily for the sake of time, so you can iterate and learn relatively rapidly several different concepts that work principally the same in two dimensions as three dimensions. However, what we would definitely need to look at to not be very out of touch with what is done in reality for the most part is we need to look at three-dimensional modeling because most things are three-dimensional in nature. Most practical problems you can't really simplify to two dimensions, unfortunately. So there are some important distinctions between two-dimensional and three-dimensional modeling, and we're going to go through some of those today. So you'll have an idea of how to do both of them and use a wide range of different setups for physics, whether it be subsonic, compressible, supersonic, thermodynamic in nature, etc. So what we're going to do here is we're going to go ahead and import a geometry file prepared later. And this will be an example of you don't just have to import the object of interest, incidentally. So let's import this, and we're going to mark all CAD edges and create one part per part surface. Click OK, and it's going to open a geometry scene for us. So you'll notice the first thing when this happens is a block came in. This doesn't look like a wing. Well, that's because we have several parts here. We have the air region, which is this block. So we imported everything. We have the wing itself, which is actually embedded in this block. Note the coordinate system. Z is up, Y is out the right wingtip, X is back along the aircraft, or along the wing. Our wing is in the middle here, and I'm just gonna, let me see here, show only the wing so we can take a look at this. We can see a couple things here. First off, it clearly has a finite wingspan. Secondly, it very clearly has some dihedral to it. The wingtips are rounded with relatively small rounds, while the actual wingtip round is quite large, but there's small rounds kind of smoothing that out. The trailing edge appears to be quite sharp. So, several things like that. Now, we're actually going to make a small change to this for the sake of time here. We are going to take this and demonstration purposes, and we're going to modify it. Oh, one other thing. We didn't just bring in the air region, which is this block minus that wing in the middle. We also brought in several regions to help us refine the mesh. You have a cone on the left wingtip, right wingtip, and just a general refinement region in proximity to the wing itself. That said, we are going to only simulate half of this wing, because theoretically, flow, even around a finite wing, should be quite symmetric. So what we're going to do here is we're going to take and note the size of this block, which is pretty much the air region. It's pretty big. It's almost 100 meters long, about 60 meters wide, or exactly 60 meters wide, and 30 meters tall. So we're going to set this to 0, which should theoretically be the half span of this wing. And we're going to click Create. And we're going to subtract the occasional typo, apparently. We are going to subtract this half region subtract away from our air region. So we selected both the air and the half subtract region, and now we do this, and we should have, oh, excuse me, where's, Okay, well, just for the sake of thoroughness, let's go ahead and extend this in those directions. So we know we're encompassing the entire air region. Let's try that again. Execute. Okay, this is curious. So let's open up a new scene here just to try and verify what the heck is going on. Because I'm pretty sure I told it to subtract. So let's see here. So if we look at just the subtract. Oh, yeah, it's showing more stuff. But there we go. Now we can see that there's a wing embedded in this thing. It still has dihedral to it. You can kind of see that even with the wall right there. Otherwise the same. So this is just half of our domain. So what we're going to do here is we're going to go ahead and kind of split up our domain so we know what the different faces are. We know this is the inlet, this is the top, this is the left wingtip boundary, this is the bottom, and this is the outlet. And then what's left over should be simply a symmetry plane, effectively, and a wing itself. Yep. So the block surface is our symmetry plane. We have a faces itself is the wing, and actually split by non-contiguous. Split by right wingtip, and this is actually the wing itself. So we rerun the subtract, and it should update the names. There we go. So we have our wing itself, and I should rename these. Boundary left and boundary right, to not make it think that this is part of the wing. There we go. A little bit of an iterative process there. And the block itself leaves us with this block surface thing right here. So there's our subtract. We're going to go ahead and assign parts to regions, create a region for each part and each part surface. So if we look at regions, we now have a subtract region. And it is showing this entire thing, but I don't think it's actually using this entire thing. Or maybe it is. That doesn't look particularly correct. Something's going on here a little bit. I'm not quite sure what. Let me show this. I think it's just a graphical bug, because if you look, if we plot this, right, it's the same. Right, or it's exactly what we'd expect. So I think that's just a graphical bug with highlighting, is what's going on here. Because if it was actually that, something would be very wrong. Let's go ahead and set some boundary conditions. We're going to go ahead and set this as a pressure outlet. This will be a velocity inlet. These will also be pressure outlets. The wing is a wall. This is not a pressure outlet. This is a symmetry plane. What this says is that the flow is going to act like there is flow on the other side of this boundary that is the exact same as the side it is simulating. Also, save often, save frequently. Let's go ahead and save this on the desktop for now. Okay. Now, here's where we start to get into things that are a little bit different. So let's go ahead and set up some physics. select models. First of all, this is not two-dimensional. This is three-dimensional. We're dealing with a gas. We're dealing with a relatively subsonic gas. We're dealing with we're going to call it an ideal gas with segregated fluid temperature. Steady flow, even though parts of the flow aren't steady and we know that, we're going to pretend like it's steady. Turbulent, K omega, that should be everything we need. Gravity's not going to really play because we're not dealing with large changes in density. So we don't need to include that. So that's our physics engine, physics model. Now let's go ahead and prepare our mesh. Well, we don't need badge for 2D meshing because we're not doing a 2D mesh. Simple enough. But we do need to set up an automated mesher. So there are a couple of ways this works a little bit fundamentally different in 3D. Meshing has two stages. It has a surface meshing or a surface remeshing phase if you enable it, which you should. And it has a core meshing phase. So for the core mesh, we're going to use a trimmed cell mesher. I'll describe what the difference between these is a little bit later. And prism layer mesher. So it'll go through in order, I believe, and execute the surface remesher, and then trim cell, and then prism layer. But now we need to do some controls here. So I'm going to... How big do we want this to be? I'm going to... 1 centimeter is going to give us... This is almost 100 meters long, give or take. So 1 centimeter would be a little bit ridiculous. Let's go with a base size of 5 centimeters. That ought to be manageable, at least. So one thing about the trim cell mesher that's important to call out is it changes the size of the cell in steps of 2. So you're going to want your minimum, maximum, every size you have, for the most part, with the exception of prism layer total thickness, you're going to want to be a binary multiple. That is, 1, 0.5, 0.25, 0.125. That is, in percentage, that would be 100%, 50%, 25, 12.5, etc., etc., etc. Or 100, 200, 400, 800, etc. So like we're gonna have a 1600% base size, which is what, like 4 doublings, 2, 4, 8, 16. So again, powers of 2 if you're using a trim cell mesher. If you're not using a trim cell mesher, this doesn't matter as much. We're going to use 8 prism layer, or excuse me, yeah, actually we'll go with 8 prism layers. We're going to turn down the surface growth rate to slow. Surface proximity doesn't matter because there's not things in proximity. And, well, I haven't put any custom controls on, but we're going to go ahead and just point this at our region, our subtract. And we're going to let it run. But before we let it run, there's an important thing to look at here. And that is that, unlike a 2D mesh, a 3D mesh can run with multiple cores, for part of it. Remember when I said it runs in steps. The surface mesh is still single-threaded. It will only ever use 1 core. However, the volume mesh, the core mesh, can use multiple cores. So I'm going to set this to parallel so it can use as many cores as I'm throwing at it, which I believe is 14. With no refinement, we'll run this and see what it looks like. This might take a minute. You can already see that this is going to take a while because I don't think I've done anything too fancy unless I've really made that size too small. And it's already taking considerably longer kind of look at the progress it's made so far, you can see it's taking considerably longer than any of the two-dimensional meshes have. So leave some more time for this one than you have previously. I'm just going to pause the recording itself here and let's keep on running in the background. And we'll come back when this is done. Just a quick addendum while we're waiting for this thing to finish still. This is the part that's single-threaded. When it says remesher or it's doing what's known as a surface mesh, that is single-threaded. The thing that is parallelized or can use multiple cores is the volume mesher, which we'll probably see show up here momentarily-ish. I'll pause it until it gets to that point, and then I'll comment on that. Okay, we can see that the surface remesher completed. If you can read that text on there, it says it completed it in approximately 480 seconds. So, what is that? 8 minutes? So that said, it's definitely taking a lot longer than you're probably used to for the 2D mesh. So now what it's doing is it's doing some preparatory steps. Scroll up here for the prism layer, creating what's known as the prism layer subsurface, and it's using all 14 cores that I've given it for this one. And this only took 23, 24 seconds. And now it's executing what's known as the volume mesh, which in this case is a trimmer mesh because that's the type of mesh we told it to use. So we'll let this finish, and then we'll come back and take a look at what it's done. So a couple remarks on the setup for this. You might have already been kind of scratching your head a little bit and going like, okay, wait a second. There aren't any custom controls on this at all, right? And I kind of waved that away as we're just giving this a first pass. But you might have also had a problem with that, and that would be for a good reason. Because custom controls do two things, right? They do many things, but they do two big things conceptually. They make cells smaller, or they make cells bigger. Turn this down just a hair. They make things bigger as well, which means that the mesh is the exact same size everywhere. Well, on one level, that's fine for the wing, probably. If anything, our mesh might be a little bit coarse for the wing. But way out at the boundaries, excuse me, that's a problem. Because we're going to have cells that are 5 millimeters, or no, 5 centimeters to a side everywhere on the boundaries of this model. Inlet, the outlet, the top, the bottom, the symmetry plane, the wingtip boundary, everything. Since we know we don't need as many cells out on these boundaries, we know we have far more cells than we actually need. It's actually just about to wrap up. So we'll pull open a mesh scene when this is done and take a look at how bad of a omission was that. I can already tell you it was a pretty bad omission. Well, for the sake of demonstration, we'll take a look once this finishes. So we can see that this took a little bit over 800 seconds all told. So 10 minutes, give or take. And it took about 2 gigabytes of memory. The total number of cells that it created is way more than it needs to be. It created 32 million cells. That's a lot. What is this? Something probably like 10 million faces. Or, sorry, 100 million faces ish. Another 37 million, um, 37 million vertices. So it's got a lot of parts. It's got way more than it needs to be. So let's take a look at this. Oh dear, that's never a good sign when it just turns out and it just looks like a black blob. This is what this looks like. That is a problem. Let's go ahead and hide that and try and find our wing in here. Okay, let's see our wing. Well, actually, our wing doesn't look too bad. Let's keep on hiding stuff, though, so we can actually see it. Show only this part. So let's see here. Where might we go? Not terrible as far as surface mesh goes. I would have actually preferred it to be a little bit finer um, on the wing, or considerably finer even. But yeah, we do not need that much stuff out on those surfaces. So now we're going to use a surface control to take a look at all those inlets, the outlets, the symmetry plane, and we are going to make it a lot bigger. So this is still a surface control. It's in 2 dimensions. This controls an edge. In 3 dimensions, this controls an entire a surface, which doesn't have to be flat, but in this case, they're all flat. And we want to change the target and minimum size. And we also want to disable prism layers. Now, I haven't gotten to actually visualizing this mesh in 3D yet, because we don't want to visualize a mesh that's this ridiculously oversized. So we're going to make the cells out on this perimeter 32 times bigger. Actually, you know what? Sorry, we're going to start with 16 times bigger, which incidentally matches the maximum cell size. So this is as big as any cell is going to get. It's a little bit less than a meter. And let's go ahead and run this mesh, and I bet you it's going to run immensely faster. We can see it's already done with the surface mesh. It's already doing the trimmer. A little bit hung up there, but hey, it's already done, and this is only about 500,000 cells. So we're actually going to tweak this a little bit. We're going to turn this down to 2 centimeters. We're going to bump this custom target size to 3,200%, as well as the maximum cell size. So the net effect is we're definitely going to have more cells, but they're going to be a lot more focused on the wing rather than in the bulk mesh. And this one I don't even need to pause because it's running fast enough. There, that looks much better. That is a lot closer to the input geometry. That's a pretty nice curve right there. Look at the leading edge. That's a pretty nice smooth curve it's got going there. The trailing edge is sharp, so we really don't need to consider that too much. But so note this is not necessarily going to be the wing that you guys get for your assignment, but this is about 1.5 million cells, which is probably about right for this. Like, you might be able to go a little bit less for something of this size, but this is probably as good as it gets for the most part. So let me restore all hidden parts so we can take a look at the walls. We can see that these are a nice uniform grid, which is actually pretty close to the way it should be. as far as sizing goes. And we can see that this grid gets much finer close to the wing. You can actually see this kind of two-dimensional imprint of the wing on this boundary surface that it interacts with. So you can see that the cells only grow in steps of 2 for the trimmer mesh, right? If it wants to make the cell bigger, it takes what would have been 4 cells and makes it 1. And if it does this step again, it does this again. It takes 4 of these cells, makes it into 1. Further up, 4 into 1. Further up still, 4 to 1, 4 to 1. I don't know if there's another step. There is not. So it only goes in steps of 2, which is why I was saying use multiples of 2 if you're using a trimmer mesh. If you're using a polyhedral mesher or a tetrahedral mesher, you don't need to go in steps of 2. But if you're using a trimmer mesh, which I personally recommend, you should. And a quick aside, the reason I recommend the trimmer mesh for this application is the flow direction is predominantly, at least for lower angles of attack, aligned with the face of this cell. You expect air to be going in through this face, leaving through this face. Very little flow moves through the upper and lower surfaces. Let me see here. Of this cell. So that's where trimmer meshers tend to excel, is where you don't expect a huge amount of non-orthogonal flow. We do expect some amount of non-orthogonality, but it's relatively limited for the bulk mesh. So this is an application reasonably well suited to this. If you had shockwaves, which were going to be highly, like on a 45 degree, and you expect flow directions to be changing from horizontal to 45 degrees, then you might need something more like a polyhedral mesher. But for something relatively low energy and fairly orthogonal like this, we can get away with the trimmer mesh, which is one of the more computationally efficient meshes. So now, how do we visualize this? Now, the thing is, we can only look at what the cells look like on surfaces right now. Like, this is a boundary, right? This is our symmetry plane. This is our inlet on the left, our outlet's on the right. This is the bottom of our domain. The top and the side are hidden. This is our wing. We can only look at the mesh on the wing so far. So let's go ahead and look at some derived parts and look at visualizing the flow around this thing on things that we don't have as surfaces. We're going to create actually a whole bunch of section planes. We can drag, we click drive part, new section plane. We can come over here and it gives us, if we have a scene up, it gives us this little GUI where we can kind of drag this around. I'm going to change this to parallel projection mode. So let's go ahead and create a couple of these. I'm going to create one down the wing this way. I clicked no displayer. Actually, you know what? Let's do existing displayer mesh one. Create. Now I want to take Y normal instead of X to create a plane that looks like this. We'll create a couple of these. Create one. Move this over a little bit. Create another one. Move this outboard some more. Create another one. Let's see if we can create one like right on this round where we know the mesh is really, really, really fine. Yeah, right about there, I'll do it. So, create. If we click close, we should see a whole bunch of planes. Aha! Perfect. Now we can see what this mesh looks like in a couple different directions. So let me show only this one. Well, we can see this cutout of our wing. It very clearly has some dihedral to it, as we knew. You can see the mesh gets really fine near the wingtips. And as we kind of grow away from the wing, it gets a lot coarser. Right? It grows in steps of 2 every, dozen cells or so. So this method of creating section planes lets us visualize things, hide some of these, that we wouldn't normally be able to see. So I'm going to hide everything that was part of the boundaries of the simulation, including the wing itself. Including the wing itself. There we go. And these planes are all direct. They're non-physical, but we can look at what the properties look like along these dimensional planes. And they don't have to be orthogonal. You can define them in any way, shape, or form you so choose. But we see what this mesh looks like everywhere. And again, it depends on where you want to look. This mesh could probably get a little bit finer on the wing. It could probably get a little bit coarser out here. But this is a pretty decent starting point. So what we're going to do here is we're going to institute a couple more controls really fast. I'm going to use a surface control on the wing, and we're going to use this for a wake refinement really fast. And this is going to be like the last thing we actually do to, extend 10 meters behind the wing in the X direction. That is exactly what we need. We'll do a 2-degree cone angle spread. The isotropic size we're going to make 200%. Slow. Okay. And I'm just going to tell this to mesh again. Execute. We'll see how long this takes. Oh, it's already. Oh, interestingly enough, you'll notice I told it to remesh, right? But it didn't redo the surface mesher. This is actually an important point. Glad I did that. I wasn't actually planning on that, but glad I did that. Notice this very first line that I've highlighted when I said execute mesh operation. It says surface remesher is up to date. It will not redo stuff that it doesn't think it needs to do. And it doesn't need to redo the surface mesh because nothing we did changed the surface mesh. Nothing we did changed the surface mesh. That's important. We can do the same thing if I add a new control really fast, a new volumetric control. Well, remember we had those refinement regions, so I'm going to actually pull in a couple of refinement regions, and we can see it highlights the region that it's going to refine the mesh in. So I'm going to just refine the trimmer mesh in this area and say it is 100%. It's not going to let the cells grow. They're going to stay at whatever that base size is. So inside of this region, which is a volume defined by these parts I made earlier, we should see the mesh remain constant. As a matter of fact, we see that it doesn't change the surface mesh again. It still finds the surface remeshers up to date. So what will change the surface mesher is things like surface growth rate, surface proximity, surface curvature, minimum size, target size. Things like that will change the surface mesh and it will need to recompute it. Things like maximum size, wake refinements in general, so isotropic size, prism layers, those will not require changing the mesh or changing the surface mesh. So it's a little bit hard to see here because it really didn't change much. So we're actually going to go ahead and turn this size down 1 notch. I'm also going to turn down the isotropic size of our wake refinement, and we'll stop messing around. This mesh might not be 100% ideal, but it'll serve to get the point across. And these things work, or these derived planes work for not just meshing and looking at the mesh. You could look at pressure on this plane, etc. Uh, so that is an important thing that is very, very, very powerful to visualize three-dimensional flows. Is being able to kind of carve it up and look at the flow wherever you want on any plane that you want. And it doesn't have to be a plane either, although planes are by far the most common. You could also, I can't actually show it now, but you could have, I believe, spherical sections. You can have cylindrical sections. You can cut the domain up into sections in different ways. Rather than just straight planar splitting. So we're going to go ahead and let this finish, which is actually about to wrap up. Take a look at it briefly, and then I'm going to try and start the simulation, get it going. I'll pause the recording so you don't have to stare at the iterations walk across the screen. And then we'll return to this to take a look at what we can do to actually take a look at what is the flow doing in 3 dimensions. The one thing I want to note is that I am going to go a little bit out of order. I am not, importantly, going to set up some stuff that I'd rather usually do recommend setting up before you start the simulation. So I'm not going to set up reports or monitors. I'm just going to get this thing running as quickly as possible for the sake of the time of the recording. So we can see that this broke, what is this? Okay, I might have gone a little bit crazy. This is about 10 million cells. This really doesn't need 10 million cells, but this should highlight the, like, we went from, what, 1.5 million cells up to, like, almost 11 million cells? And we didn't really change that much. We just changed this area here, but this is a volume. It's actually a pretty big volume. So volume controls will scale the number of cells you have stupid quickly. Like, this went up by about a factor of like 8. And oh hey, what we did primarily was we had the number of cells in this region, and also we added some more cells out here. So using volume refinements can get you in trouble really quickly because of the square cube law and exponential scaling. So be mindful of that. We're going to just take a kind of a fairly standard 10 meters per second here. How long is this going to take per? Longer than I'd like. Okay, so what I'm going to do is I'm going to back off that volume refinement. And if I tell it to run, oh wait, I need to tell it to remesh first. So that's fine. So let's tell it to remesh. It's gonna run through its remesher really fast here. And then I'm going to tell it to run, and I'm just going to pause the recording while leaving the simulation going. And we'll come back and take a look at how to visualize some of the flow properties on this. Oh, but incidentally, this should also be an example that you don't need to reset the simulation when you change a mesh, because I ran the simulation for like 3 or 4 steps and remeshed, and it's figuring it out just fine. So there we go. That's much better. This will get through 1,000 iterations in not too much time. So I'm going to pause the recording here, and we'll come back to this a little bit later. Okay, we've come back to this, I don't know, an hour later, give or take. Done a couple thousand iterations. This looks solidly converged. This has probably been what I would consider converged. Well, this is residuals, so I want to caution that we're not looking at lift or drag or any of that other good stuff. But from a pure residual perspective, this looks like it's probably been done since about iteration 800, give or take. Um, Most things have fallen a couple of orders of magnitude. Energy is relatively high. That's not a particular surprise because not much is going on in terms of energy. Turbulent kinetic energy is relatively high. The rest of these residuals have dropped. You know, 4, almost 5 orders of magnitude. Some of them have dropped 5. One of them is almost 6 orders of magnitude. So that's reasonable convergence, I think. Let's take a look at some scalar scenes. So, first off, let's take a look here. Let's take a look at some of our derived parts. I'm just going to show all of our derived planes, and we're going to look at static pressure. So we can look at what does pressure look like on any of these planes, right? Remember, these aren't surfaces. There is no random wall in our simulation that looks like that, right? There's nothing physical here. We're just looking at sections of the simulation. So we can see the pressure distribution over our wing. We have high pressure underneath. It falls off as we get closer to the wingtip. We get low pressure on top. Again, it falls off as we get to the wingtip. And we can see an extreme low pressure region kind of right near the wingtip. That probably surmise that that's the formation of a wingtip vortex right there. And if we show these other planes, we can see that that wake region is not present closer to the wing root. Like we see this at the wingtip, but as we hide this, we can see we don't have that pronounced effect as much. We can kind of see it a little bit here, but only a little bit, and it's basically non-existent back here. And we can see a wake region extending way back. So we can see, again, with section planes and section geometry, things in 3 dimensions that we would normally not see because they're not on surfaces. That said, this is not everything. So we're going to talk a little bit about some of the other derived parts because those are really the primary way we visualize stuff. And that is going to be a couple things here. We can do, we'll start with the obvious one, the big one. These are streamlines. Streamlines follow the path of the flow. So what we're going to do here is we're going to select a point seed. And what this does is, well, actually, we have a couple different ways of defining this. Let me go through this. We have point seed, which you pick a point in 3-dimensional space. In this case, we probably want to do, so z equals 0 is the leading edge. So we probably want to do y equals, oh god, I don't even remember what the span of this thing is. Let's try and snap this to our wing. So what I'm trying to do is put this a little ways upstream. Oh, no, never mind. That's what I need to do. Let's not bother snapping apart. So let's go a little bit upstream of our wing. Right about there-ish. And we'll move this slightly further upstream. So this is basically 1 meter in front of the wing, at the wingtip, give or take. And we're going to seed points in a 10-centimeter diameter sphere. We're going to seed 20 points. Great. I'm going to close this for a second. And if I hide these, we can see that we have a whole bunch of lines that show the path of the flow. Specifically, they show the path of the flow through this wingtip vortex. So I'm going to add to this scalar scene, I'm going to add a surface displayer. And we're going to show what does this wing look like. Let me see here. Geometry. There we go. So this is what our wing looks like. So we can see these streamlines move over the wing and have that nicely formed wingtip vortex downstream of the wing. This is the path the flow is following there. There's other ways of making streamlines. Let's go back, streamline. Let's do a line seed instead. And I'm using the display tool option so we can see where the end points of this line are. So we're going to, again, do this about 1 meter upstream. So -1, -1. We're going to do this at about half span, give or take. So and then we're going to extend from, we're going to go from about 1 to -1 meters. And we can do 30 lines. So this will spread 30 streamlines created between those 2 points vertically. And actually, we might want to go a little bit more outward than that. -2.25. There we go. So this is going to spread, in this case, -2. There we go. This is going to spread 30 streamlines between those 2 points in a line. We're going to create a new streamline displayer. So we can see that they're a lot more nicely ordered, but oh hey, these are still affected by the wingtip vortex. And you can color these streamlines by whatever you want. So we can color them by static pressure, again, just like the other one. And we can see where in that streamline is the pressure low, where is it high, etc. So streamlines are a beautiful tool to visualize the flow in 3 dimensions, because how else would you know the flow was doing this, really, other than just following it in 3-dimensional space? One thing I want to note is if you have something like this, where you have multiple scenes showing the same thing, these are all showing static pressure, you probably want to make it so that the color bar, or excuse me, the scalar field of all of these is set to the same min and max. So let's do 85 to 60. And if these are all the same limits, then you can hide the extra color bars. And this color bar properly represents the pressure on all of these. So streamlines are very, very, very powerful. You can also, if you wish, this is not going to work as well in our case, you can also seed streamlines on, where's my drive parts? You can also seed streamlines on a part. So in this case, let's go ahead and select, let's see here, just the wing surface, I guess. And it basically puts some streamlines on the surface of the wing, and it's trying to follow them downstream. Now, it didn't actually put very many, you'll notice, but it definitely put some of these streamlines on the surface of the wing and then follows the flow downstream from there. Some of these get caught up in the trailing vortex. Some of these just proceed downstream. But in any case, you can see the path of the flow takes. So you can use a part seed where you place them on a part. You can use a point seed where you place them in a certain radius of a point. That was the wingtip one. This was within 10 centimeters of a point that we chose. You can place them on a line. And those are the main options you have for placing streamlines. Now, I do want to note something else here. Streamlines, you'll notice these aren't going upstream. Right? I place them in a point here and they go one direction. That's not necessary. I can absolutely have these go both forward and backwards. So in this case, letting the streamlines go backwards, let me hide this for a second, up to the beginning of the domain. Or I could ask it to just go backwards only, not go forwards at all. You can see the and right there. or forward only. So you can have them go backwards, forwards, etc. You can control how far they propagate. In this case, I believe this is 190 meters is the maximum distance those will flow. How many steps it will use to integrate to find them. The point seed is where is it seeded? In this case, at a point. How big is the radius? How many of them are there? Which vector field is it following? If you have it follow a vorticity vector field, it looks all kinds of wacky, right? Velocity is the usual one that you use for streamlines because that actually visually tells you where it's going. But you could technically use any vector field you so chose. Wouldn't be very good necessarily, but you absolutely could. So streamlines are one of the big ones. There are a couple others that are more specialized. There is things that are called isosurfaces. Well, what are isosurfaces? They are surfaces of constant value. Isosurface. So if I say negative 20 Pascal isosurface in this domain, so in the subtract, which is this air domain, we're looking for a constant value of static pressure. And this exists in the range of negative 110 to approximately 60. So we're going to do negative 20 pascals. And I hit create. Well, what does this show us? This shows us a surface where everywhere on this surface, the pressure is negative 20 pascals. So you can see this is the region on the wing that is encapsulated by this, that has a pressure that is, or this is the boundary between below negative 20 pascals and above negative 20 pascals. Gauge. We could change this value, make it, let's say, negative 30, and this should shrink it. Negative 60 is going to be a very small region, right? You can see this is the only area on this wing, a little bit in that vortex, that has a pressure below that negative 60 pascals. Or I could do 10 pascals. Oh, hey, we're looking at the bottom of the wing all of a sudden. Little bit at the trailing edge. So, right, you have a region at the trailing edge, you have a region at the leading edge. These are regions that are, or this surface bounds the area that is above 10 to below 10 pascals. So isosurfaces are also good ways to visualize complex flow and find regions that are of interest to you. So if I wanted to know where the flow is, less than or more than 20 pascals or whatever I said, more than 10 pascals, this absolutely does a beautiful job of just saying, okay, great, where is this true? It's in that area. You know it's in that area. Very easy, very quick to see. Again, it depends on the question you want to answer, right? A couple of streamlines, an isosurface can very easily tell you a lot about the flow. Now, I do want to make a comment here about streamlines because depending on what you're doing, and they might actually change this from looking at this, but let's take a look here. Oh, perfect. Okay, they actually changed this. It used to not be this way. Clearly, it's been a while since I've done streamlines because I haven't done it with this version of Star. But it used to be that streamlines, let me go ahead and set all of these streamlines, came in as true streamlines, where they were infinitely thin lines. Those are kind of hard to see. But stream tubes are actual finite thickness tubes where you can look at the flow and the path it's taking. So you can think of stream tubes as finite thickness streamlines. Now, if you look really closely, you'll notice that along the tube, right, it's definitely varying. If I make this really big, I think you might even be able to see something else. Let's go 0.15. Make these really fat stream tubes. Oh, never mind. I stand slightly corrected. But stream tubes are generally the way to look at it because you can see a finite thickness tube much more easily than an infinitely thin line. And I think one of these was a line. That needs to be a tube. You can also have stream ribbons, which is kind of a hybrid between the two. It's a two-dimensional flat surface. You can think of it as a streamer. You can kind of see that where it's a flat surface. That's also an option, but stream tubes tends to be a little bit better. Ribbons can be useful though because it also shows you that this flow has vorticity to it because the ribbon itself is rotating. You can't tell if a tube rotates, right? So those are some very powerful ways to visualize flow in 3 dimensions. And a finite wing, similar to this, but not this, is what you'll get for the final assignment to look at 3-dimensional model. You probably only need a million and change cells, maybe ish. I wouldn't go less than a million, but I wouldn't go more than like 2 and change unless you're feeling particularly ambitious. Um, but there are many ways to visualize 3-dimensional flows, and they're primarily involving derived parts to get sections, whether it's a section plane, whether it's a section cylinder, a section sphere, or a constrained plane, which is actually a kind of interesting one, which is effectively the same thing as a section plane. Let me go ahead and try and move this over here. The difference, this is a quick addendum that I wasn't actually planning on adding on, but the difference between a constrained plane and a section plane is that a section plane extends to infinity. A constrained plane exists only in the area you define. So this plane shows us only the flow in that little box that I just drew. Let me take a look. Static pressure. Excuse me, why isn't this only this part? Oh, because this is just geometry is the reason why it's not showing me anything on here. But a constrained plane is effectively a section plane that isn't infinite. It only exists in a constrained area. Those are the big ones. So isosurface, you have sections, you have streamlines. You also have constrained streamlines, which are kind of the same. And you can also do a vortex core, which will attempt to show you where the core of a vortex is. So very obviously, we have a strong vortex out here by the wingtip. And we also have a little bit of vortex going on at the trailing edge as the flow kind of wraps around the back surface of that trailing edge a little bit. But you can also have a vortex core to show you where a vortex is in the flow. That's another somewhat relevant one. Those are the big ones. You could also use threshold parts. So, I'm trying to come up with, let's say this is going to be similar to an isosurface, but like for example, we could say everything where pressure is between -10 and -20 pascals, it's going to highlight them. So we can see that this area, everywhere that's been shaded in, has a pressure between those ranges. Well, if I'm feeling particularly ambitious, I can say everything that's below minimum. Well, hey, that's the inside. Or I can say above maximum, and that's damn near everything. Right, that's going to be near everything. You can see there's a little bit missing in the middle here. It's kind of hard to see, but it is in there. Or you can say everything between those ranges. So threshold parts, which shows you everywhere where things exist either between, above, below, or outside of a range you specify. You have section planes, you have isosurfaces, and you have streamlines. Those are some of the big tools you have to visualize complex 3-dimensional flow phenomena that would otherwise be very difficult to represent. So hopefully that helped. This is about an hour long at this point, so I'll leave it here. That's kind of the highlights of the big differences between 2 and 3D. As you can see, the setup is very similar. There's a couple things that are simpler, but you have to be really cautious about refining your mesh in 3 dimensions because it can be really easy to accidentally get too many cells. So be mindful of your controls. If you think it's taking too long to mesh, cancel it, make your base size bigger, and try again. Better to start too big and make it finer than have to accidentally sit there for 3 hours looking at a mesh that you're going to have to redo because it's too fine, right? That doesn't serve anyone. So for the mesh, start coarse and work your way fine rather than the reverse because it's going to be more time efficient. Other than that, I think that should just about be it. I'm going to go ahead and stop it here, and we will talk more about this in class.